Chapter 12: Access and Interconnection Technologies. Major areas we're going to be talking about are upstreams and downstreams, our narrowband, and our broadband technologies. That includes our older technologies such as local loop ISDNs, some of our newer technologies like DSL, and all of the different characteristics of DSL like ADSL and HDSL and HVDSL and all the different variations of DSL. Transitioning from that into cable technology, normally referred to as broadband, but not 100%. After that, we're going to talk about data rates within the cable modem, cable standards. From there, fiber or some form of hybrid fiber / coax examples. That's always a good one nowadays. We're going to transition into flat out just fiber. Once we're done with that, we're going to go back into some more terminology, wireless, then our capacity for our connections, and that includes things like our circuit termination, our termination for our DMARCs, our DSUs, our CSUs, basic telephone systems, and then just back into some more additional standards. Sadly, with this chapter, there is no getting away from standards. There are so many standards that are out there that we may or may not encounter that we have to be able to cover them. Alright, so let's talk about the basics of this chapter. A big part of that is, again, discussing our narrowband versus our broadband. And that includes all of the technology that may be within those two examples. We're also going to talk about how our ISPs leave us circuits to allow us to do interconnections between our business and other businesses. And basically just kind of how an ISP functions. Not super in-depth, but at least a basic overview. The last thing we're going to talk about is, again, how data communication communicates. So, access technologies normally refer to sometimes data, sometimes telephone, but some form of data communication that allows us to connect to a provider to share network-based resources. So essentially what that really means is we connect to a service provider that allows us a network connectivity to their network. I have Coax, for example. I pay Coax $100 a month to connect to their network. Coax, in turn, connects to other networks. So I can go through the internet through them. They are my internet provider, or ISP, internet service provider. Now I can do this in one of two ways. That $100 access fee allows me to kind of pick and choose my speeds. I can have a symmetrical line, and that is my upload and download are identical. Or I can have an asymmetrical line, and that's where one might be faster than the other. But before we can answer that, what is upload or what is download? Sometimes you'll see them upstream versus downstream. Doesn't really matter, it's the same dang thing. So downstream actually is the information from the ISP to you. The upstream is the information to the ISP. Okay. For example, you want a web page. You go to Google. You actually go to your web browser, type google.com, hit enter. That will actually send a upstream request to your ISP that will send the request to Google's web server. The download portion of that would be the actual web page. So then the question then becomes, well, are they the same size? Do I need symmetrical or asymmetrical? Okay. Realistically, for most home users, your upload will always be slower than your download. The reason behind that is you're only going to be requesting so much, and the content you're requesting is always going to typically be larger. Thus, you need more download speed than upload speed. Here's a graphical representation of that. I'm going to pause it for 1 second to kick my dogs out, so give me 1 minute. So it's important to grasp the concept of upstream and downstream, because it is very subjective. Because what happens if we're looking at this from the web server's perspective? Your request as a end user, you'd upload it to your ISP. Your ISP would download it to the web server. The web server would upload your website to the ISP, and from the ISP to you would download it. So upload and download is very subjective, depending on the perspective that you're looking at. And what about from the ISP's perspective? That's a whole another argument that I'm not even going to touch. But a big part of this is just recognizing that upload and download are sometimes very subjective. So now to our narrowband and broadband access technologies. So normally our narrowband are classified in lower band bandwidth. But what is bandwidth? Bandwidth is actually typically referred to as our data rate. So the important part here to recognize is bandwidth is actually the theoretical maximum amount of data that can be sent. So the maximum data rate that data could be sent. Throughput is the actual data rate. The reason you have to distinguish between the two is I pay for a 100 megabit connection from Coax. If I get 90 and there's 10 megs of overhead, that's still my 100 megabit bandwidth. So bandwidth is just, again, the theoretical maximum, or is the maximum. Throughput is the actual, because you may have some error or overhead that doesn't allow you to achieve your maximum bandwidth. So that's an important concept to understand. So our first narrowband technology is our traditional telephone dial-up connections, our 56K modems. Sadly, some people still use them. AOL still is in existence, and they're alive and kicking, so that's really weird. Another form of narrowband technology is our leased circuits, and those are not a dedicated circuit. That could be a shared circuit. So you could actually be sharing a connection in an office building, for example. Now this is different than the concept of a shared circuit for cable technology, because there's a broadband technology that also does these circuits, but in a different way. Fractional T1s. So last week we talked about the bonding and how bonding the 56K modems allow you to do a T1. So a fractional T1 is just a percentage of a T1. So again, that's going to be a leased circuit. One of the last ones are ISDNs, or other forms of telecom data services that are pretty much old and slow. That's what our narrowband typically is. Those are our older and slower technologies. Our broadband technologies could be anything faster than a T1. A T1 kind of could be called broadband, but you have to have the full speed of the T1. And even then, with nowadays standards, that's really slow. DSL technology, or cable. Again, cable is sometimes referred to as broadband. Even though these are all broadband, normally when you say cable or cable modem, that's an automatic broadband. And then wireless, because there's multiple types of wireless now, but we're going to have to cover a few of those. So, what's an ISDN? Local loops and ISDNs are, so a local loop is just a massive loop around an area that ties back to a phone company's central office. And they only use two cables. So a pair of cable. And what they're doing is they're allowing people to directly connect back to that central office. That would allow you to get a better internet connection. Again, this is one of our narrowband technologies, so this is an older technology. And what they would do is, if that was not fast enough, is they would allow you to bond some of the cables together. For an ISDN, it's 2B and 1D lines. So 2B plus D. So then the next question is, what's a B line? A B line is actually a 64 kilobit per second connection. What ends up happening is you would actually bond those two together to have a 128 kilobit per second connection. But you have to have a way to control it, hence the D channel or the D line, which is a control channel of 16 kilobits per second. It was a way to do faster connections. So once we understand the basic principles for our CO and our ISDN connections, we can actually move back into the realm of DSL. While DSL is classified as a broadband technology, it's really built off of the narrowband. Because again, it's basically an ISDN, just manipulated just a little bit. So the different variations are ADSL or asymmetrical DSL. After that, we move to symmetrical DSL. Okay, remember, symmetrical means the same bandwidth both ways. After that, they realized that we needed to go more than 2 or 3 miles away from our location, so they actually did HDSL or HDDSL, and this is just high bit rate, and that actually allowed businesses to go up to 3 miles. You could get it further, it's just the further away you went, the crappier the service got. Then they have the VDSL, or very high bit rate, and that allows them to do 52 megabits per second. There are some hybrid technologies where they are like SHV DSL. Some of them are hard to find documentation on, some of them are just plain kooky ideas. But there are several types of DSL out there. That was the point of this. So how does DSL actually work? DSL uses a type of multiplexing that would be frequency division multiplexing. And what it does is, because we have that one phone line coming in, we have to use it for multiple areas. They actually do frequency division. So 0 to 4 kilohertz, that's our regular phone. 26 to 137, that is our upstream. And from 138 to 1100, that's our downstream. Notice our downstream compared to our upstream. Our downstream is way larger than our upstream, because again, this is an asymmetrical line. This concept is done regardless if it's DSL or cable broadband. They do just different forms of frequency division multiplexing so that you can do voice, video, and data. For the cable example, that would be VoIP or telephone, upload and downstream for our data, plus video dealing with our just regular TV. And again, that's just another form of frequency division. Also, this does not illustrate the guard bands. Because we're doing frequency division, the guard bands are still there. A common question is, well, why are they wasting between 4 and 26? It's not wasted. They do a large guard band there so that we can better filter out the different frequencies. We have to recognize a few other things. This is always really funny. They say DSL is complex because none of the local loops will have the same characteristics. With DSL, it's all subjective based on the situation of the CO or the local loops. That is why you can have varying experiences with DSL. Another one is DSL uses discrete multitone modulation. It's a form of, or combination thereof, frequency division multiplexing that allows for the inverse of multiplexing. So what the hell does that actually mean? All that really means is they will take those streaming connections and they can break them down into subchannels so that we could have better downloads and better upload speeds. On top of that, they will allow you to do separation of data. Give me one more second, I do apologize for this. Going back to our DSL, one of the important things to recognize for our DSL is here they actually set or reserve two channels of upstream information for control data. So they break them up into subchannels for better control. Essentially what they allow you to do is the best performance without using less than the 26 kilohertz, because that's when you get the slower connection speeds. What they also do is if a particular ratio or a particular frequency has a lot of noise on it, it allows you to encode bits at a different rate. But you do have to recognize that the quality on a given frequency may be low, and thus ADSL modulation could actually encode fewer bits per baud, thus making it a little bit slower connection. So with DSL, it's not always as straightforward as it may seem. So let's talk about the data rates of our ADSL, or DSL in general. So again, this is an older technology, so it's still a broadband, but still fairly older technology. We're looking at between 8 and 9 megs of download speed and of 640 kilobits of upload speed. Though, again, these numbers are so skewed. ADSL 2 can download at 20 megabits per second. We're in Las Vegas, we have CenturyLink Business, and we have some connections that allow you to download at 48 megabits per second. And it's just a hybrid of ADSL. So with DSL, it really all depends on your area and the characteristics of that local loop in your area. So there is no hard and fast rule of thumb of the speed for DSL. Check your area, they'll tell you the rates, and go from there. How is ADSL installed? Because again, it does do voice and video, well, could do video, but it does do voice and data at least. You have to have a device called a splitter. The splitter actually allows you to filter out traffic. Here is a great example. The splitter is on the inside of the house. The splitter filters out traffic one way for the phone and the higher frequencies for the DSL modem. What that allows you to do is talk on the phone without getting the higher frequencies, so you don't get the frequency buzzes or hums. Also allows the DSL modem not to get any of the lower frequencies. That way they're only dealing with the higher frequencies. It allows for a best in performance. Moving on from that to our cable technology. Our cable technology actually allows for the use of a community antenna television system. Basically your Coax. It still uses frequency division multiplexing. It still allows you to send voice, video, and data. It does do higher bandwidth and it is less susceptible to magnetic interference. It doesn't use twisted pair, it just uses a single copper core. And it does use multiple frequencies. So our current cable modem standard, DOCSIS, is our version 3 standard. Our version 3 standard allows us to go to 150 megabits per second. This one says 52 megabits per second. This is probably using a different DOCSIS standard. However, we actually just introduced a DOCSIS 3.1 standard, and that allows for 10 gigabit per second connections. We probably will never see that in our lifetime. We may be, who knows. But right now, our average connection for broadband, we're talking between 100 and 150 megabits per second. Now, our broadband or our cable is normally defined as a shared subscription or subscriber line. So what ends up happening is it used to have a coax cable brought into a housing community. Then that housing community actually would connect to that shared cable via a junction box. So if you have 10 houses in a housing community, all 10 of them would be sharing that one cable. That's no longer the case. It's no longer copper being ran into that box. It's a high-speed fiber connection. That junction box is you still do share that junction box with your neighbors, but you all get a dedicated frequency on that fiber line. That allows for the higher sustainable speeds than traditional cable lines. Again, this is a newer technology. So again, that whole, if you have N subscribers or you have N connections in your community, and that'll be 1 divided by N, that's how much capacity you get, that's no longer valid. Most cable companies moved away from that. They're doing just fiber to a junction box, and from that junction box to your house will be dedicated connection lines. The reason that's important is a lot of people said that broadband or the cable was slower. It really isn't anymore. Let's say it's a 10 gigabit connection line and there's 10 houses that have cable on it. Theoretically, you could have 10 people, each with a 1 gigabit connection or 1000 megabit connection, and that would still fit on that 10 gigabit line back to the cable company. And they don't do lots of houses per junction. They do pretty small sections of buildings on a junction. No. The cable modem installation is pretty straightforward. You plug in the coax cable, plug in the power, you're pretty much good to go. But the question I have, which is a very common misconception, is where does the cable company have to stop? So when you have cable installed in your house, the DMARC actually is your cable modem. The cable company is responsible for the cable into your house, only to your modem. Legally, then they have to stop. However, most cable companies won't stop just at your modem. They'll go a little bit further just to make sure you're having better service. But legally, they don't have to. That is actually known as the demarcation or the DMARC. And that's where, again, legally they're no longer responsible. So what is that fiber connection from the junction box back to the cable company? That's called a trunk. And then that junction box is our feeder circuit, or our centralized circuit. And then the individual connections from that junction box to us normally could be referred to as a feeder, or could be referred to as the last mile. Normally that junction box is within a mile of your home. Normally it's a lot closer than that, but it can be anywhere up to a mile away. Notice that we're moving into the hybrid fiber coax connection, because again, they moved away from copper all the way through, and now it's fiber and then copper. Here is again graphical representation. Junction box for a neighborhood. From that junction box to the house, it's coax. from that junction box back to the provider is all fiber. Why do they do this? It's all about faster speeds. The FCC actually created what we know as the broadband plan, and that is actually to get gigabit internet speed to everyone. So how many types of hybrid fiber technologies are there? We have fiber to the curb, fiber to the building, fiber to the home, fiber to the premise. What's the difference? Fiber to the building versus fiber to the home. Same thing. Normally, fiber to the premise is the generic term that encompasses all of them. These are so convoluted, and when you do more research into these are I would not trust. Like fiber to the building allows for higher upstream. Fiber to the home has higher downstream. Honestly, when I contacted our ISPs here, both Coax and CenturyLink, they're the same speeds. Or you have the ability to pay for a varying speed depending on what your needs were. So all of this deals with our high-end system. We already talked about the DOCSIS standard. We actually are on the tail end, so we as an end user get the tail end of that connection. This entire wiring system actually relies on the cable modem termination system, or CMTS, and that actually used to be where the coax would come together at the ISP's office and from there connect to their network. Because it's all fiber based now, it's still a cable modem termination system, it's just no longer using copper, now it's using fiber. Our DOCSIS is not just our data standard, it also has to do with requested services, like pay-per-view. So how is access in rural areas done? DSL can only go a few miles. Cable could go a little further, or fiber, just that gets expensive. One way is actually to do wireless. And what type of wireless would allow us to do that? We'd be looking at our 3/4G services, our cellular data, or our WiMAX. Our WiMAX is, again, just our analog TV that was converted from analog TV to data. That's actually, the infrastructure is already there, so why not reuse it? And then lastly, our satellite. Satellite has a higher delay, not the fastest speeds, but faster than 56K modem, definitely. But satellite is susceptible to the environmental noise. Same thing with WiMAX. WiMAX also is affected by environmental noise. Like if it's super cloudy and super stormy, you're not getting fast internet service. So we already talked about the last mile. So why do we care about our internet connection at home? So we're seeing more and more SOHOs. That actually is a small office or home office. And that is people that are working remotely. For example, I'm at home. My office for this job is at my house. I have a day job where I have a physical office, but we aren't tied to physical offices anymore unless we have a physical job. So let's cover a few more different types of different terminology. Core or backbone. And those are actually our super high-speed interconnects. So we talked about a 10 gig connection from our junction box back to our ISP. That would be a trunk. But what about between our ISP and their ISP? They're going to have a backbone, and that's going to probably be like a bundle of 10 gigabit connections. We're talking like 10, 20 gigabit connections, not just a single one. Our ISP has an ISP. Our ISP's ISP has an ISP. We actually have a tiered system. Normally, end users connect to a tier 3 provider. Tier 3 providers connect to a tier 2 provider, a Tier 2 provider connects multiple Tier 3 providers. Our Tier 2 guy gets their internet from a Tier 1 person. That Tier 1 person connects to several Tier 2 and to all the major Tier 1 providers. So how many Tier 1 providers are there? If you look up major Tier 1 providers, there can be anywhere between 7 and 10 companies. Those are the major telecom companies like AT&T or Time Warner or XO. Those are the major companies that deal with our interconnections. Here's a graphical representation. Now again, a 10 gigabit connection, that's no longer the case. We're looking at a 10 gig connection per junction box. So probably make that a 100 gig connection, if not more. So if what would happen if we need a 10 gigabit connection, we could actually do a point-to-point leased circuit. That is where we pay our ISP a high fee for them to give us a point-to-point circuit that gives us a faster connection. You can get nowadays any type of circuit that you need. It just depends on how much you want to pay. We actually were just offered a 100 gigabit connection, and that was like a $20,000 a month connection. What really was going on was they wanted us to get 10 gigabit connections that were bonded together, but again, it's expensive. Though, if we got a leased line, we have to actually follow their agreement. And that also includes to the different standards about digitizing our data. So we actually have a specialized device that does the conversions for us. A DSU/CSU, Data Service Unit to Channel Service Unit. A lot of our leased lines, they break everything into channels or different frequencies. So our DSU/CSU actually does do the termination or the media. I can't think of the dang word now. Our media changer. That way we can go from one technology to another technology. Normally our CSUs also do contain a loopback so that we can test it. That also allows us to do balancing for guaranteed of service. Again, our CSU is the channel portion. Our DSU is our data portion. Our data portion deals with digital formatting and things like that. Our CSU takes the formatting and does the frequency or the different channels, or also known as our encoding. We already talked about our DMARC. We already talked about our different types of standards. We did not talk about our NIC. I don't understand why they like to change these terminology, but Network Interface Unit or Network Interface Card allows us to have a boundary from one network to another network, or from one device to another device for communication, or to give us internet or network connectivity. Now that could be internet connectivity or network connectivity. Granted, yes, the internet is just a large network, so we could probably say just network interface unit or network interface card, and that would denote internet as well. It's just sometimes the textbook likes to go between both of them. And again, this is our dealing with our DMARC. That is between two networks, our ISP's network and our network. The separation point is actually our DMARC. That is again the boundary that for the equipment, where they're responsible to where we're responsible. So are there other types of circuits out there? So we didn't really talk about T1s or E1s. So what are those? So our basic data rate, our basic frequency is 64 kilohertz, or 0.0464 megabits per second, and that is essentially one voice circuit. A T1 is a bonded 24 connection. Don't forget, we have to have 2 dedicated services for error checking, so that actually is 26 total. So it's not 26 voice, it's 24 voice plus 2 error or control data circuits for 26 total. T2s, there's 96, for T3, 672, but those are all just American standards. In Europe, they have completely different standards. They have the E system. Again, 30 voice circuits. I believe that's 32 or 33 for voice plus 2 or 3 for error control, so forth and so forth. So why do we have these? These were back early 90s, mid 90s, early 2000s, when we didn't have our high quality broadband. That was back when T1 was 1.5445 megabits per second, and that was amazing fast. Now you can get that same speed for about $5 a month. That's no longer realistic for the type of speed that we need. Our broadband is, again, even a cheap broadband is 5 megabits per second down, 1 megabit per second up. Our high-speed broadband, that could be anywhere from 150 megabits down to 50 up, or at least in our area, we have gigabit fiber, so that's 1,000 megabits down and 1,000 megabits up. You don't actually get that. You get 1,000 down and like 500 megabits up. But I mean, our T series, our E series of lines aren't really fast anymore. But we still classify them as fast services. And they're really not. We do have a few other standards like our SDS services, and those are actually dealing with our faster than gigabit speeds, because we had to have a better connection. So our STS connection, which is a copper-based cable for, let's say, gigabit, that's an STS-24. That is 1.2 gigabits per second, or 19,440 voice circuits, plus, again, the error controls. So, is there an optical version of that? Sure. Those are called OC lines. Here, our base data rate is roughly 51.84 megabits per second. So, to go from an OC1 to an OC3, it's roughly 3 times. To go from an OC3 to an OC12, that's roughly 4 times. Not again 100% 4, but I mean, when you start adding them up, they pretty much add up pretty closely. From 1 to 3, there's a factor of 3 there, so you times it by 3. From 3 to 12, it's a factor of 4. From 12 to 24, it's a factor of 2. From 24 to 48, it's a factor of 2. And again, when you start looking at these are normally whatever the factor is. From 1 to 3 for the OC lines, factor of 3. So you get your OC1 line, times it by your factor, 3. That's how you get your OC3 line, 155. Between OC3 and OC12, factor of 4. So you'd take your OC3 line, times it by 4. That's how you get your OC12 line, so forth. There is a distinction between STS and OC. OC is optical carrier. STS is copper-based. Okay, actually, we only have one slide left, and that deals with specifically our synchronous optical network, or our SONET. And that is our synchronous optical connections. And this is a basic frame for our SONET. We could actually send a optical connection through a copper-based signal. Because again, the media for the payload or the media for the frame or packet doesn't matter. It's going to be the same regardless. That's because we have standards. Here we have 90 columns of data with 9 rows. That makes up our SONET frame. We can send this frame over an STS connection. It's the same. And that actually concludes our PowerPoint for today. If you have any questions, please let me know. If you have any concerns or issues, again, please let me know. I hope you guys have a great afternoon. Thank you and good